Hi everybody, welcome to lecture 27, Electrical Engineering 331. In this lecture we'll talk a little bit more about stability. Okay, so let's jump right into this. I've labeled this as example 27.1, but 27.1 actually is the only example, but it contains, I guess you might call, subcases of it. So however you want to regard this. What you're asked to do is to investigate the poles of the transfer function of the following circuit. And we have not used that terminology before about poles, but what we're talking about is if you have the transfer function of a system, and in fact, let me go all the way to the end of this lecture. So suppose that we have a transfer function and it's written in this form: h of s is equal to n of s divided by d of s, where n of s and d of s are polynomials in s, and the degree of the numerator is strictly less than the degree of the denominator. Then the poles of the transfer function are simply the zeros of d of s. In other words, it's the values of s for which the denominator will go to 0. And of course, one way to find those zeros is to factor the denominator, and of course we have seen that by factoring the denominator we can then find out the inverse Laplace transform of this transfer function, which of course would be the impulse response of the system. And so that, as we already know, that gives us insight into the stability of the system. So we're going to be talking more about those ideas in this lecture. Okay, so this is the system under consideration, and we're going to initially carry L and C along in the calculation, but at the end we will use L equals C equals 1 in order to make the analysis a little bit easier. And what we're going to be thinking about is the idea of varying R. R will initially be a somewhat larger positive number, and then we will investigate what happens as we decrease the value of R. Okay, so V out is defined as the voltage across the capacitor, and you have Vn as shown here. Now, I hope that you are able to look at this circuit and see that this is simply a voltage divider, and the transfer function will simply be the impedance of this capacitor divided by the entire impedance. And if you can see that, then immediately you will have, just by inspection, you see that the transfer function of this system is 1 over Cs, which is the impedance of the capacitor, divided by R plus Ls plus 1 over Cs, which is the impedance of all three elements added together. Now, if you don't see that, I will show you how to get it, but as you will see, the derivation of that result is much more lengthy, and so it would really be worthwhile, if you have forgotten what voltage dividers look like, to refresh your memory on that, because it would be very nice for you to be able to just get the transfer function by inspection in this way. But again, if you don't remember how to do that, then the way we would do it is the following. Kirchhoff's voltage law would tell us that Vn of t minus R times I of t. By the way, I've defined I of t to be the current flowing clockwise in this circuit. So Vn of t minus R, I of t minus L di dt minus 1 over c times the integral from minus infinity to t of I of tau d tau is equal to 0. And furthermore, V out of t is the voltage across the capacitor, which is 1 over c times the integral minus infinity to t of I of tau d tau. Now in both of these equations, the term 1 over c integral minus infinity to t of I of tau d tau appears, so let's work on that term a little bit and try to simplify it. Well, first of all, we notice that we can break up the integral from negative infinity to t into two integrals, one from 0 minus to t and one from minus infinity to 0 minus. And the reason to do that is that if you look on your tables in chapter 3, you don't have an entry for the Laplace transform of this entire integral, but you do have an entry for the Laplace transform of this. So that's the motivation for breaking up the integral in this way. Okay, now the second thing, to go from this line to this line, we have that the integral of the current from negative infinity, so from the beginning of time up until 0 minus, well, that would just be the charge on the capacitor at time t equals 0 minus. Okay, then let's go ahead and multiply this 1 over c times everything in the brackets, and you can see that the second term will be qc of 0 minus over c, which is the same thing as simply vc of 0 minus. And then this term is like this. So when we substitute that in into both of these equations right up here, then they will become these two equations right here. And now we're ready to go ahead and take the Laplace transform of both equations, and when we do that, we will get this. Now, one thing to note is that this Vc of 0 minus, which is just a constant, we're treating that as Vc of 0 minus times u of t, because u of t, for t greater than 0, that's a constant, and so we're treating it as Vc of 0 minus times u of t, and so therefore, when we take the Laplace transform, we get Vc of 0 minus over s. Everything else, I think, is pretty clear. The Laplace transform of this di dt is s I of s minus I of 0 minus. That's in table, one of your two tables in chapter 3. So, otherwise, these are just the two equations that we get by Laplace transforming these two equations. Now, it's important to remember that when we're looking for the impulse response or the transfer function, we take all initial conditions to be 0. So this Vc of 0 minus over s is 0, Vc of 0 minus over s is 0, I of 0 minus is 0, and so this simplifies the equations significantly, and the two equations, once we set all the initial conditions to 0, they would just become this. And then if we solve the first equation for I of s, we will get this. And notice that the second equation tells us that V out is equal to 1 over Cs times I of s, so which we have right here. So that would just be V out is equal to this. And then finally, H of s is V out of s divided by V in of s. And so that will be 1 over Cs divided by R plus Ls plus 1 over Cs, which is the same result we obtained before by looking at this as a voltage divider. But you see how much quicker that was. So again, take a look at that and make sure you understand it. But however you get the result, we have this, and then what I will do is here I will go ahead and take the CS down to the bottom, And so I get 1 over LCS squared plus RCS plus 1. And then if I take an LC out of the denominator, I'll get 1 over LC times 1 over S squared plus R over LS plus 1 over LC. Now, we could continue to analyze this with all of those variables, but it gets a little tedious, and so what we'll do is we'll go ahead and stick in the values L equals C equals 1, but we'll keep R so that we can easily see what happens as we vary R. So when we take L equals C equals 1, we get this very simple expression for H of S is equal to 1 over S squared plus RS plus 1. And you might remember that one way to go about factoring something like this is the method you might have seen in elementary school called completing the square. We will take S plus R over 2 squared, because that would give us, when we square this, we would get S squared, first term squared would give us that, and then multiply the first times the second, double it, and that would give us the RS. But then we would also get an R over 2 quantity squared out of there, so we want to subtract that off and then bring down the 1. So this is another way of writing the transfer function of this system. And now that we see that, we have 3 cases that we can consider, depending on whether this stuff out here is negative, 0, or positive. So let's see how it goes. So if R squared is greater than 4, like I said, we're thinking of R as initially being somewhat larger, but then going to 0. So I'm going to initially think that R squared is greater than 4. Then I'll look at R squared equals 4, and then I'll look at what happens if R squared is less than 4. Okay. So for case number 1, R squared greater than 4. Okay, to help you see what's going on here, I'd like to pick a definite value of R greater than 4, a definite value of R that will make R squared greater than 4. So I decided to pick R equals 2 times the square root of 10, because when we square that, we would get 4 times 10, or 40, and certainly that's greater than 4. So we'll pick R equals 2 times the square root of 10. Now, when we stick that into this expression for H of S, we get S plus R over 2, so that would be S plus square root of 10 squared. And then let's see, R over 2 would be square root of 10. We square that, we get 10, so here we have a minus 10 plus 1, or a minus 9. So that's how we get this expression right here. And we notice that this, since 9 is simply 3 squared, this is the difference of 2 squares. So we have S plus square root of 10 plus 3 times S plus square root of 10 minus 3. So in this case, the 2 poles are negative square root of 10 plus or minus 3. And H of t, the corresponding impulse response, would be A times e to the minus square root of 10 minus 3t plus b e to the minus square root of 10 plus 3t, u of t. And the important thing here to note is that we have 2 distinct roots, and both of them are real roots, and both of them are negative. And this is corresponding to a BI/BO stable system. And whenever, for this particular problem, whenever R squared is greater than 4, you're going to get 2 distinct negative real roots. Okay? And in each, you'll always have a BI/BO stable system in case 1. Okay, well, let's look at case 2, R squared equals 4. Well, if R squared is equal to 4, as long as this is a real resistor, then R must be equal to positive 2. And so h of s then would be 1 over s squared plus 2s plus 1. That's from right here. So h of s would be 1 over s squared plus 2s plus 1. And so that's, of course, 1 over s plus 1 squared, which means that in this case, the poles are -1 and -1. We have a repeated root, and we know that in that case, the impulse response, h of t, would be t e to the minus t u of t. And so what we conclude then is that in case 2, we have 2 repeated negative real roots. So 2 negative real roots again, but this time they're repeated. But again, we have a BIBO stable system. So finally, let's look at case 3. Remember that case 3 here is where r squared is less than 4. And so I'll pick something very easy, r equals 1. Certainly r squared then is less than 4. Well, if I pick r is equal to 1, then h of s is 1 over s squared plus s plus 1. And so doing the usual trick of completing the square, we see that h of s could be written as 1 over s plus 1/2 quantity squared plus 3/2, or in other words, 1 over s plus 1/2 quantity squared plus square root of 3 over 2 squared. So that means that h of s will factor, the denominator will factor into s plus 1/2 plus j times the square root of 3 over 2 times s plus 1/2 minus j times the square root of 3 over 2. And so we have two poles here. S equals -1/2 plus or minus j times the square root of 3 over 2. And you might remember that, that this form right here corresponds to h of t equals e to the minus t over 2 times a sine square root of 3 over 2t plus b cosine square root of 3 over 2t u of t. I'm not going to worry about finding a and b because that's not important. I just want you to see the general form here. And so in this case, where r squared was less than 4, we get two complex conjugate roots. But again, the real parts are negative, and we still have a BIBO stable system. So as long as r is a positive real number, which of course it would be in any physical system because r represents resistance, then we will have, and as long as we have this circuit right up here, we would have BIBO stability, all three cases. But what happens if we take away the resistor? Now we can model that by just setting r equal to 0. And if we set r equal to 0 in the transfer function, in this case, it would just become h of s equals 1 over s squared plus 1, which would mean that h of t, the impulse response, is sine t u of t. Now, we know that that is not absolutely integrable, and so therefore this system is not BIBO stable. And what's interesting is that if we look at the poles of this transfer function, they are plus and minus j. They no longer have a positive real part. In fact, the real part is 0. These two poles are on the imaginary axis. So when we were getting poles with negative real parts, we had BIBO stability. When we get these poles that are on the imaginary axis, we don't have BIBO stability. Now, on the other hand, this function is not increasing as t goes to infinity, but it simply is not decreasing either. It's not absolutely integrable. And so some people, when the poles are on the imaginary axis like this, and maybe you could also have poles, some other poles that were to the left, in other words, have real parts that are negative. In any case like that, that's referred to as marginal stability. So if these were the only two poles, this is a marginally stable system. Now finally, I'd like to consider what would happen. This is a non-physical case because you can't get a negative resistor, but think about what would happen if we did allow R to become negative. Well, in that case, we would find that the real parts of the poles would be positive, and h of t would be growing in magnitude as t goes to infinity. And so that's neither BIBO stable nor marginally stable. So what we conclude then from all of this is that, again, if we let h of s equal n of s over d of s, where n and d are polynomials in s, and the degree of n is less than the degree of d, then if all of the poles have negative real parts, the system is BIBO stable. If some of the poles are on the imaginary axis, but no poles are in the right half plane, in other words, no poles have positive real parts, then the system is marginally stable. And finally, if one or more poles are in the right half plane, in other words, if you have even a single pole that has a positive real part, then the system is neither BIBO nor marginally stable. So that is a little more review of stability, and we have introduced this new term of marginal stability. That is the end of discussion for lecture 27. So good luck.